With this device, I can switch devices on my boat, and yes, there are 12 volts, and this is capable to it. And the MOSFET will switch on and give the 12 volts to a few extra parts. The first part is a PPTC. This is a self-resetting fuse from 5 ampere. The second part is a normal fuse, because if the PPTC fails, I want the current is also off. This fuse is 10 amperes because I never want to change it, and I wanted the PPTC always get off first. Hello and welcome back. I have made this fantastic device. This is the switching module for my board computer project. With this device, I can switch devices on my boat, and yes, they are 12 volts, and this is capable to it. And it can read out sensors like vlotters in Dutch. I don't know the English word. In this video, I will tell you how this works, how I made this thing, and how I plan to use it with a cheap yellow display in the future, because my goal is to possible replace my board computer itself by a cheap yellow display. I am Brendan Koster and this is Brendan in Tech. Let's start with a very short recap of my board computer project. On my boat come some sensors, and I want them to have a message on my phone when there is something wrong, like water into my boat. To connect those two, I use a module. I come back on it later. That have to connect to Wi-Fi, have a touchscreen, and because it's so complicated at the moment, I thought I would also switch devices with it. I use a shift register to switch those devices and also to read out sensors. I use the Raspberry Pi Pico as microcontroller for it. If we simplify this, we can say we have the board computer, the Raspberry Pi, on one side and the shift registers on the other. To can connect those on a long distance, I added two Smith trigger inverters. This clean up the signal so it is possible. I connect everything, and now it's also possible to add a second Smith trigger inverter and connect it to the next module. That for a short recap of my board computer project. The device I've made now is in fact the shift registers with some electronics around to make it more functional on my boat. The device works quite simple and intuitive. You add power, and that's a voltage that depends on the insert of the module. In my case, it's 12 volts. You connect via the UTP cable the board computer. The board computer gets power over the UTP cable, so there are no other connections needed to the board computer module. And the board computer will say via the UTP cable which of the ports have to be available for an output. That output have a current of at highest 5 amperes. It's also possible to do it the other way around. Like you have a vlotter and you use these ports as an input. And it can be that you use 1, 2, and 3 as output and 4, 5, and 6 as input, or how you want to do it. For testing and showing, I have this setup: the switching module, the board computer. They are connected via an UTP cable to 12-volt lights, an adapter for 12 volt with one small loose cable for faking an plotter, and let's see what happens. On the display I have a lot of buttons. They are bad to see, sadly, but I can use them to switch one of the lights on. You see the light go on. I can also switch the other light on. As you see, you have to put the button a long time, but that is now and that is a software thing, so that can be better. On the display, you can see 8 dots. When I connect the loose cable with one of the inputs, then you see one of the black dots disappear. Actually, it will be a white dot, but that's hard to see on camera. Let's see it. And when I connect it to another, then you see another. Before we going to the inside of the switching module, a thing that I think a lot of people are very excited about: the cheap yellow display. This is a display with an ESP32 on the back, and everything should work fine. One problem on this thing is there are quite limited GPIO ports, and the ports that are available on it are certainly not capable to work with 12 volt, I think. Uh, Actually, they are not capable to work with 5 volt, and 12 volt is very, very too much. And one thing, there are too limited GPIO ports to connect them good to my switching module. That's why I have also built this thing. This is one UTP port on one side, and on the other side a small GST 125 connector. This connector has 4 pins, and I have a microcontroller inside. That microcontroller can communicate via serial print statements with the cheap yellow display, and on the other side connect to my switching module via UTP. This is still work in progress, but I know it have to work because I have done something like this with another microcontroller. Now I think it's time to go inside of the switching module. Inside the switching module are two PCBs. The first one, the blue one, is the logic PCB. Here are 5 integrated circuits, and in a video on my old channel I've explained how this works. So for now I will leave a link in the description of this video so you can see that. But if you want the best explaining of these ICs, I will recommend to see the video of Bill from the Dronbotworkshop, and he explains it fantastic. The second PCB, the yellow one, is the switching PCB. This PCB translates low voltage, low current signals, 3.3 volts and very low currents, to high voltage, high currents. However, 12 volts, 5 ampere, it is not very high voltage. and not very high current. But in the microcontroller world, it is extremely high. Both are connected with a 30-pin flat cable. This sounds a lot, but I want the signal in both ways. That the logic side can tell the switching side which ports have to be switched, and also the switching side can tell the logic side on which ports are power. And there is a little bit of power management between both boards, and I want that the switching side can tell the logic side that it is a switching side. On the back of the PCB, I've written where each pin is meant for. So the outside four are for letting the other PCB know what this PCB is. The pins more inside are for power, logic voltage and ground. Then on both sides 8 pins for data. The pins on the outside are for data that goes out this PCB, and the pins on the inside goes for data that goes into this PCB. And the middle two pins are for 12 volts, so that's also transferred from the one to the other PCB. This same information stands on the other PCB also, and it is also that the outer pins are for information that goes out, and the inner pins are for information that goes in. So if you lay them on each other, it will be a perfect match. On the other side of this PCB, also the back side, is also written where each pin on the outgoing port is meant for. This is the ingoing and this is outgoing. This will connect to the board computer or the previous switching module, and this will connect to the next switching module. As you can see, I have here a wire because I was wrong in one connection and I didn't connect the microcontroller in pin that's written as MCY, uh, and I have made that extra connection. Sorry, if you download this Gerber files and let print this PCB, you know you have to make this one extra connection. Looking on the front side, you see that the actual PCB where everything happened is quite small. However, the integrated circuits I used here are the biggest that I can find. They are still quite small. Left of the actual PCB is some extra add-on option. So it is possible to connect a Wi-Fi chip or to connect a SPI for if you replace this HC74 12 chip with an 80 tiny. But I do not have tested one of those, so I don't know if it works. On the top side of the PCB, to call it so, I have three options for outside connections. The highest is the UTP. The position under is one GST125 and one UTP port. And the lowest connection are two 10 pins, so I can connect there everything and raw wires to debug, trialing, uh, prototyping, etc. An important thing for every PCB is a little power management. In this case, every IC have a small capacitor. And by the outside connections, I have small parts soldered. These are PPTCs. These are self-resetting fuses. And I have made a jumper, a solder jumper, and in this case I have let open the 3-volt 3 or the logic voltage and close the 12 volt. This for the inside, and for the outside I will open the 3-volt tree. No 3-volt tree in because I have here a buck converter, and the buck converter will convert 12 volt to 3-volt tree. I don't know how powerful this is, and I think he can do a few switching modules, but not a lot. So I recommend to have two, maybe three switching modules with one buck converter and then solder a new buck converter in the next switching module if you need more. And from the board computer itself, I recommend to use at highest one switching module without buck converter because the buck converter in there is from the Raspberry Pi Pico and that's not powerful at all. Switching on my switching PCB, I do as follow. I use a P-channel MOSFET. These MOSFETs have a gate, a drain and a source. Because this is a P-channel, I connect the source with 12 volts and the drain I connect to a load. The other side of this load I will connect to ground, and I use this port as input also, but that has nothing to do with the MOSFET. The gate of the MOSFET is connected to a resistor, and the end of the resistor is connected to another resistor that is connected to 12 volt again, because if there is 12 volt on the gate, the MOSFET will be off. To turn the MOSFET on, I use a NPN BGT. This has a base, a committer and an emitter, and because of this is an NPN, the committer will connect to ground, the emitter will connect to the resistor, and if this is active, there will be ground 0 volts on the resistor. Because this is very high resistance, this will do nothing, so there is 0 volts and the MOSFET is turned fully on. The base of the NPN BGT I have to connect to a resistor, and the end of the resistor is my input from 3.3 or 5 volts. To read back the input here, if I use this as an input, I will use a voltage divider. These are two resistors and it works quite easy, so on the internet you can see a lot of it. First I use a very high 1 mega ohm resistor, a second a 330k resistor that I connect to ground, and in between the voltage will be around a quarter of the original input. So here is a safe readout point for 3.3 or 5 volt devices. Now we have seen this all. I think it's a nice time to go to the real PCB. On the switching PCB, I've used the most primitive components I know: transistors and resistors. These small ones are bipolar junction transistors or BJTs. The big ones are metal oxide field effect transistors or MOSFETs. Simply explained, a transistor, and it's so well a MOSFET as a BJT, is a switch. And for the switch you need a resistor. First the signal comes in, that goes through the resistor, through the BJT. This is a NPN BJT, that means that with a positive signal it switched a negative signal. If the negative signal is on, then it will give the negative signal through this resistor to the MOSFET, and the MOSFET will switch on and give the 12 volt through the outside. In between comes at the moment. Here is a pull-up resistor, a very high 10k pull-up resistor. If the BJT is off, because of the pull-up resistor, there will be 12 volts on the gate and the switch of the MOSFET is off and there is no current goes outside. After the MOSFETs, the current will go through a few extra parts. The first part is a PPTC. This is a self-resetting fuse from 5 ampere. The second part is a normal fuse, because if the PPTC fails, I want the current is also off. This fuse is 10 amperes because I never want to change it and I wanted the PPTC always get off first. The last part is a diode. The diode will protect the circuit if you connect a motor to outside and turn it off. This is because the motor will create a current if it's spontaneously turned off, and that's not good for your circuit. From this point, there is also a little wire goes back to the top of the PCB. And here are two resistors. These two resistors together is a voltage divider. So the voltage of 12 volts here is here around 3.3 volts. And that's safe for the microcontroller. I think it's obvious. I say resistor, but I mean resistor array. But it explains a lot easier if it is one. But here is a set of 4 lines, resistor arrays, resistors, transistors, etc. And on the other side is exactly the same. So in total 8 lines, and here in the bottom are 8 MOSFETs. Good to know if you rebuild this and use my Gerber files. I have forgotten here a via. To solve this problem, I can connect it to the ground from this side of the resistor array. It's not a problem if you make a bridge to the ground of the BGT, and the problem is fixed and everything works fine. The last component is this PPTC, a 0.5 amperes. It's to give 12 volts to the other side of the switching module. And this PPTC have to protect it that if the wire here is broken, that I'm not able to get 5 ampere of current through the thin wires of everything else, through the UTP cables, and have a big problem. So very important, this PPTC, a very low current. That was everything for today. If you want to know more about the switching module or anything else from my board computer project, please let me know in the comments of this video. In the next video, I will talk about the module that connects the switching module to the GPIO display. So the GPIO display, or one bigger family of it, can replace my board computer itself, and it's easier to rebuild. I hope my video was very interesting for you, that you have learned something from it. However, thanks for watching, and I hope to see you in a new video. Goodbye!